So with that, now that we have some background looking into what a population is, I want to get into quantifying alleles. How do we quantify alleles in a population to say, yes, evolution is occurring, or no, evolution is not occurring? So the first thing we need to learn is allele frequency. This is how often a particular allele occurs in the population. Now, keep this in mind. For most alleles, and the ones that you're going to see on the AP exam, the ones you're going to see most often we're dealing with 2 alleles per loci. Okay, so we have a dominant allele and we have a recessive allele. We're not getting into any funky genetics in terms of alleles. We're just dealing with dominant and recessiveness. So normally we assign P for the dominant allele as the variable. We assign Q as the recessive allele variable. So if we have 2 alleles for that loci in a population, both of those frequency added together must equal 1. Or if we're looking in terms of percentages, the percentage of P plus the percentage of Q must equal 100%. But normally we just deal with frequency, and that is the decimal form of how often it occurs in the population, not percentage. So we can use this allele frequency data from a real population and compare it to data to a hypothetical population that is not changing for that particular loci. That means no evolution is going on in our hypothetical scenario. So if we get no differences in our real population data and our hypothetical population data, if there are no differences between those allele frequency, then no evolution has occurred. No allele frequency has changed. The differences between real data and hypothetical data means that the population is evolving. So if you get different values between your real data, your real population, and your hypothetical population, if there are differences between what you should expect, then the population is considered to be evolving. There are changes. And so then what you want to do is find out what is the cause of this allele frequency change. Why is this population evolving? Is there something different in the environment?
So the Hardy-Weinberg conditions and the Hardy-Weinberg equation are really important for comparing what's going on in an actual population. The conditions for Hardy-Weinberg in that equation are going to show us differences between the allele frequencies of this hypothetical population and the actual population. Depending upon how big those differences are, it's going to show us if evolution is occurring and why evolution is occurring in that population.
So let's review the Hardy-Weinberg conditions. You cannot have any changes to the allele frequency, so no mutations because they can alter the allele frequency. Random mating has to occur. So it doesn't matter who's that they mate with anybody. We'll talk about sexual dimorphism in a little bit. No natural selection, no adaptive change to that population. And differential survival cannot occur in your hypothetical population. You have to have an extremely large population size. This is going to lead to stability. The more alleles you have, the more stable your allele frequencies are. And lastly, no gene flow. There is no new immigration or emigration. There's no movement into or out of the populations. So we're not going to change allele frequencies that way. So these are 5 conditions for your hypothetical non-evolving population. Okay, so you want to assume the population is in Hardy-Weinberg equilibrium. So looking at this data, what I want you to notice is, Remember, you have 2 individuals per loci. If you are given the total number of individuals, you can calculate P and Q directly. You have to remember that everybody has 2 alleles per loci. So the number of individuals you have must be doubled. So in this population, we have 500 individuals, but we have 1,000 alleles. So to count for my dominant Y, I have to take those that are homozygous for dominant Y and multiply that by 2. So 245 times 2 gives me 490. I also have to add in that dominant Y from my heterozygotes. You can't forget about those. And because they only have 1, I can add up the number of heterozygous individuals. So 490 plus 210 give me 700 dominant alleles. I do the same thing for my recessive allele. I have 45 who are homozygous recessive, so I want to multiply that by 2. That gives me 90. I add in my 1 Y allele from my heterozygote, 210. So 210 plus 90 gives me 300. So the next step, once you find the number of alleles for the dominant allele, once you find the number of alleles for your recessive allele, then you're going to take the next step and you're going to divide these values by the total number of alleles, and that will give you your frequency. I want you to pay attention to these numbers. Okay, this is my parent generation, and we're going to see what happens to the offspring generation to see if it's going to change.